So is there any query related to the previous lectures? Okay, so today again we are going to discuss about the backgrounds and fundamentals of remote sensing. So today we will cover the energy sources. We will discuss about the different radiation principles through which a particular energy source generate the electromagnetic radiation. Okay, so as we know that the meaning of remote sensing is just to sense uh, uh, kind of information or sense, let's say, a kind of sound, okay, without touching that particular object or without just being close to that source. Okay, so like non-contact information we can obtain, like hearing, its ability to listen the sound, okay, due to vibrations that occurred at some distant location. Fine. Similarly, we can feel the shock waves. But in remote sensing, where we visualize the information by seeing that, so there is the role of electromagnetic waves. So energy which is coming within electromagnetic radiation, they are sensed. Okay. So in remote sensing, our concern is to analyze the electromagnetic radiation, okay, and to learn about the different object of interest. Specifically, we consider the geospatial object. So I already told you, like, you need to remember the different wave bands which are there in the electromagnetic spectrum. Okay. So as you see in the diagram along the wavelength axis, there are many bands uh, from cosmic rays to radio waves. Okay, and we have already discussed about the background, like for the remote sensing, which particular band we need to consider. Okay, so mainly we focus in visual spectrum, and if we consider our own eyes, our own sensing organs, okay, specifically eyes, so they are sensitive in only visible spectrum. Okay, so we see the photograph, we see the object, and the reflected energy that is coming from that object, that is sensed only within the visual spectrum. Okay, if you see in the diagram, so we have three specific bands within visual spectrum. They are blue, green, and red. Okay, in terms of wavelength, so the blue band lies between 0.4 to 0.5 micrometer, while green lies in middle of visual spectrum, extending from zero point 0.5 to 0.6 micrometer. And in case of red, the wavelength is highest compared to blue and green, and the bandwidth is 0.6 to 0.7. It's 0.1 micrometer. Fine. Now further, the object information that is received in terms of reflected energy or radiated energy, they are sensed in longer wavelengths, okay, extending away from the visible spectrum. So artificial remote sensing sensors, they sense the energy outside of visible spectrum towards higher wavelength, like near infrared band. You can see mid infrared band. Then we talk thermal infrared, and it goes to microwave. So what I expect from you, you need to remember these bands and their characteristic. Okay, characteristic means where they lies on wavelength axis. Okay, so on in the electromagnetic spectrum, where that particular band is confined, what is the wavelength range? Okay, and because it is important aspect to understand the sensors which are designed. Like I discussed before, if we consider our eyes, so our eyes has a filtering ability, and it filter out all the energy which is coming from the object outside the visual spectrum. So our eyes only allow the energy within the visible zero point 0.4 to zero point 0.7 micrometer, and further internal processing is done to see the color of the object, to see the photograph. Similarly, uh, the artificial sensing systems are designed. Okay, they are the filter. So that particular, if I talk about one particular sensor, okay, and let's say that sensor is tuned in green band, okay, so there are electronic component. That electronic component only allow energy to pass through within the green band, and it filter out all other bands outside that the range of green. Okay. Similarly, if you have a other sensor and it is designed at some other location in the electromagnetic spectrum, so that sensor will only filter the energy within that particular specific band. So on the basis of number of bands, we categorize the remote sensing techniques, satellite remote sensing techniques. Okay. So we learn about it. What do we mean by panchromatic remote sensing? What do we mean by multispectral sensing? What do we mean by hyperspectral sensing? Okay. And how they are different on the basis of number of spectral bands which are used. So right now, I hope you understand the meaning of spectral bands over here. If there is any query related to this electromagnetic spectrum, understanding of spectral bands, okay, how the sensors are designed on the basis of selected spectral band, you can again discuss with me. Though I think many times since the beginning of this course lectures, I have discussed about it. Okay. So one, as I suggested you to kindly go through the unit 1 at least, that is an introduction uh, for 2 and 3 reference books, uh, mainly this Lillesand and Kiefer. So I hope you have been reading the unit 1 so that you can able to connect with this course. You can able to just see the what are the terminology we use in this course, what are the basic fundamentals of physics are there, okay, and how they are incorporated in the application specific to the remote sensing based applications and designing of sensors, etc.
Hello, sir.
Yes.
Sir, by cosmic rays, what does it mean?
Cosmic rays, it has very low wavelength, and Earth's atmosphere doesn't allow to pass through. So in remote sensing, we do not consider this. Similarly, the gamma rays, X rays, they are trapped in the upper atmosphere. They do not come, they do not enter into the Earth atmosphere. Even till ultraviolet, all the energy components, they are trapped, they are blocked. So if you see, I will come to that point later, like electromagnetic spectrum, uh, how much energy if we talk at a different wavelength. So what are the ranges of wavelength in which the energy is generated from the energy source, specifically sun, okay, and they travel, they emanates outside from the energy source, then they enters into the Earth atmosphere, how atmosphere behaves, okay, and finally the resultant energy after passing through the Earth atmosphere, the resultant energy reaches to the Earth surface. That will be discussed. Okay, so there is a generic query based on this electromagnetic spectrum. If let's say we move away towards longer wavelength, let's say away from the visible towards microwave, what will be the property of energy content within a particular wavelength?
Sir, high
Energy will be
wavelength.
more.
One by
Low
one,
energy.
Abhijit, yeah, please continue.
Sir, energy will be more because wavelength is short, amplitude will be high.
No, we are moving away from the visual spectrum towards microwave. Yes,
Lambda
yeah,
Sir,
Bhagat.
energy equals to h mu, h nu.
Yes,
So, sir, velocity of
h
the
nu.
particles will be very high.
H nu, that is Sc by lambda. It means energy component. When we define energy component at a particular wavelength, so there these two variables are inversely proportional. So if wavelength will be high, then energy will be less in one particular photon for that particular wavelength. Is it clear? So when we move away from the visible towards the higher wavelength, so in one particular photon, what will happen? Energy will decrease. Okay. So this is also one of the aspect which we consider. Okay. To define certain properties or certain parameters using which we define quality of image. Okay. This will be discussed later on. So on the basis of this diagram, there are certain uh, understanding you can develop, like understanding of correlation of name with the magnitude of wavelength, okay, as well as the magnitude of energy for a particular photon. Got it? One discussion, the previous concept which we discussed, I would like to correlate over here. Previously, we discussed about a pixel. Fine. So the pixel is the representation of a ground area element. That is the smallest ground area element. Okay. So that is a fixed area on the ground that is sensed, uniquely sensed by the sensor. Okay. And total amount of energy that is coming from that area element, that energy magnitude is calculated and a particular digital number is assigned. Fine. Now the digital number is assigned on the basis of total magnitude, total energy that is coming out from that area element. If we sense the same area element at a higher wavelength, so what will happen? The energy component will decrease. So area element is same, okay, but if you are sensing at a different spectral bands, I hope there is a clarity for a spectral band. Spectral band is defined where we are in electromagnetic radiation, where we are designing our sensor. So that is an electromagnetic band, spectral band. So in a different spectral band, energy coming from the ground area element is different. And if you move towards higher wavelength, what will happen? Energy will decrease. So I expect you to make it note on this. As I suggested you, like you need to have a notebook for this course, and I expect you after the lecture you write it down, all the discussion which we have. And additionally, you have a video lecture, you have a PPT, you have a books. Okay, but still that handwritten notes at your end is required. Okay. So this analysis I will take up later on when I will discuss certain parameters to characterize the quality of image. Okay. Moving next to our discussion. This is an entire workflow of satellite-based imaging system. So just see what are the different steps which are involved. Okay, while collection of digital images. We have already discussed this earlier. Briefly, I will go through this. So steps are given in terms of nomenclature A, B, C, D till I. Okay. So the first step A is what is the source of energy which we are considering. So in this workflow, source of energy is considered as sun. Then energy emanates outward towards sun. So Earth is there. Okay. Earth rotates around the sun. So Earth atmospheres also receive the energy coming out from the sun. Okay. Part of wavelength is blocked outside the Earth atmosphere, like all the wavelengths, shorter wavelengths, which are having wavelength less than visible, they are blocked. So the Earth atmosphere only allow the wavelength within visible, and higher than that. Now we see how that energy at a different wavelength propagates to the atmosphere. So we'll analyze the behavior of atmosphere. Then further, the resultant energy reaches to the Earth's surface. Okay. After reaching to the Earth's surface, that energy interact with the Earth's surface material. So we'll see that how that energy interact with Earth's surface materials, and certain brief discussion I have already done previously. So that will further help you to connect with the discussion. Then there is a outgoing energy from that material. So outgoing energy will have the reflected as well as radiated component. I will distinguish between these two, reflected and radiated component. Then further, the outgoing energy, that energy which is after the interaction, the energy which is going outward from the Earth surface features or material. Okay, they again passes through the atmosphere. That is step B, retransmission to the atmosphere. Okay, and now that energy is sensed by the sensor integrated with the either airborne or satellite based platform. Airborne means we have a platform, it's an aircraft or helicopter based platform, and satellite, we have a satellite that revolves around the Earth's surface. Okay, in the previous in the Friday discussion, I already summarized what are the differences between airborne platform and satellite based platform, why we prefer the satellite based platform over the airborne platform. Reason is very clear. In satellite, if we want to collect the images using the airborne platform, so again you need to plan the flight survey. Okay, you need to fly that particular aircraft and you need to collect the images. So this process is not so easy. But in case of satellite based imaging, once you install the satellite in a specific orbit, it is continuously revolving around the Earth's surface and continuously providing you the image data. So there is no need to again plan the flight, this flight survey, and again no need to fly this aircraft to collect the images. Okay, and even there is a requirement of some manpower resources. Okay, but in case of satellite imaging, all these things are not required. So there is a benefit of satellite based imaging over airborne imaging. But there are certain benefits of airborne imaging also, like we get good quality image data in case of airborne platform. Okay, because the image is captured from low altitude, so obviously the quality of image will be good compared to the satellite based platform. Fine. So after collecting the image data, after collecting the image data, where we sense the gridded ground area element, like the area which is under the imaging. Okay, that entire area is gridded into smaller ground area element. Okay, so the all ground area element energy information is collected, and subsequently a distinct DN number is assigned for each ground area element in the image data. Fine. So uh, the step F is the sensing products. What we get? So we get the images, and at each location, that is XY location, that location indicate the location on the ground surface. Okay, so uh, the area under the consideration is gridded into the smaller ground area element, and each ground area element location information is there in the image data. Okay, as well as what is the size of that area element. Fine. So along with the size of area element and what is the coordinate, a pixel value is assigned. So that pixel value is stored in binary format. Okay, but for the representation we in decimal format we discuss. Okay, so number system format, storage is in binary format, but when we do the analysis we do in decimal number system format. Okay, then if you talk this step G, there we do the interpretation and analysis. So like if you want to extract certain information, then that is done at this step G. Now finally, for application oriented information product we'll have at step G, and this will be finally utilized by the user at step I. Okay. So this is the entire workflow through which we work. Okay, so in this course we mainly concentrate on till step F. Okay, and some brief discussion will do for step G. Okay, now this step G include the image processing. When we talk, if our sensing product is images, then at step G we apply different image processing techniques to get the desired information or to improve the quality of image for further visualization and interpretation. Okay, so brief discussion we'll do in this course, and in second semester course you will learn in detail in satellite image processing course. Okay, what we will do at step G. Fine. Now at step H we have an information product that is used by the user. So this is entirely of a GIS component. So in this semester you are learning about GIS technology, and say, one advanced web GIS course you will learn in second semester. Okay, so these two courses incorporate the different analysis part at step H and I. Okay, because once you are ready with the information product, what you will do with that? Okay, for different user oriented applications. Fine. Now when we consider this GPS course, geospatial data processing, you are learning right now. So that GDP, now once you get the sensing product, what are the mathematical aspect to analyze the sensing product? Okay, yeah, there are different sense of to generate the sensing product. If we consider the geometric information, right now in the context of images we are talking about radiometric information, mainly the pixels, including the geometric information in terms of their location, XY value. Fine. When we consider the GNSS technology over here, so obviously all these steps will change, but workflow is nearly same. The sequence of workflow is nearly same, but the analysis part will be different. Okay. Similarly, so there is a, in the first semester course we have a GDP, geospatial data processing, where you will learn about a different mathematical aspect are different concepts, specifically the mathematical concepts, which we use for data processing. Okay, so we have many sensing products, vary from images to photograph, location information to LiDAR point cloud data, okay, etc. And in the second semester, related to the location information or understanding the GNSS technology, there will be the course GPS technology. Okay, and when we consider the sensing product, the complete three-dimensional information of the object. Okay, as I discussed before, if we consider our eyes, so our eyes can also sense the 3D of the object. We have a depth perception. Okay, so that concept can be has been already applied. Okay, and there is a remote sensing technique called LiDAR technology, where we collect a three-dimensional coordinate data, okay, from the object. So that data we generally call point cloud data in 3D. That is a type of sensing product. Okay, and we do the interpretation at step G, and this course you will learn again in the second semester. But in this semester, in this particular course, we will have a brief discussion on the LiDAR technology. Fine. So all the advanced courses that you will learn in the second semester, their brief discussion will be done in this course, as you can also see in the syllabus. Okay, so that is listed there. Fine. So there are two components of remote sensing system. The first one is a data acquisition system. If you see the previous diagram, so till is from A to E sensing system. This is called as data acquisition system. And after that, we have the data analysis system, where we store the data, we interpret, and further we process it. Okay, so in this image, I'm not going to discuss in much detail because most of the part we have already discussed previously. Just to this diagram, you need to understand what kind of energy is collected at the sensor. Okay, as you see that when energy comes from the sun, when it enters the earth atmosphere, that energy at a different wavelength also interact with the earth atmospheric particles, clouds, etc. Okay, so the yellow lines indicate the energy coming from the sun. Okay, now the red light indicate the reflected energy component. Previously I told that total energy going upward, a total outgoing energy from ground area element, and I told that that outgoing energy is constituted by the radiated as well as the reflected energy. Okay, so in this case, the red lines indicate the reflected energy component, but blue line indicate the radiated component. Okay, we will have discussion on this. What do we mean by radiated component and what is the reflected component? Okay, so both energy components are collected at the satellite onboard sensors, and they are processed for representing the geospatial geo information in terms of pixels. So through this diagram, and I hope it is clear that the energy comes from the sun, enters the earth atmosphere, then that energy component also interact with the earth atmosphere, particles, clouds, water vapor, etc. And the the resultant energy reaches to the earth surface object. It interacts with the earth surface materials, objects. Okay, And there are two types of energy component which further constitute the outgoing energy component towards the satellite based sensor. And the two types of energy which are outgoing from the Earth's surface object toward the sensor are radiated energy, that is shown over here in the blue color, and the reflected energy, that is shown over here in red color. Okay, so we have two types of remote sensing systems: active system and passive system. You already know what are the difference between these two. In case of passive, the sensor system doesn't has its own energy source. It relies on external energy source. While in case of active system, it has its own energy source. So mostly for the remote sensing, we consider sun is used as external energy source. Okay, but obviously there are other artificial sources which are also used in active remote sensing system. Okay, and even the many objects also serve as a source, energy source. Okay, to radiating the energy component. Okay, we will also discuss about it. So there are mainly three energy source we have discussed, like the artificial sources. If you collect the images using camera in night, and if you use the flash, so that is artificial source, and it is active remote sensing. Now sun is used as a energy source in many remote sensing techniques. Okay, and we also consider if a particular object uh, is also radiate the energy in a particular situation. Okay, we will discuss about that in which condition, in which situation the object starts radiating the energy. Okay, and that act as an energy source. Okay, so to discuss about the energy component at a particular wavelength, first we consider the energy within the one particular photon. So as we have discussed before, if a wavelength is long, then energy within a particular photon is less. What is implication of this? When we consider the radiated energy from the earth, radiated and emitted, these two terminology are same. So energy emitted or radiated from the earth's surface in thermal infrared band is sensed, while it can't be sensed in microwave. Okay, because we don't have a radiated component in microwave from the earth's surface. Okay, so if our sensor only sense the emitted component, then in case of earth we have the available sufficient energy in thermal infrared band. Okay, now to sense longer wavelength, longer areas need to be viewed. I think again we have already to understand this particular implication, you have already enough background on this. Who is going to tell me why to sense the wavelength, to sense the energy at longer wavelength, we need to consider the sensor needs to view the larger area? Who is going to tell me?
So please pardon the question.
Justification of second implication. Just read the sentence and justify it. I hope you can see that statement on your screen. What is the
Hello,
justification
sir.
for this? Yes.
Hello, sir. Sir,
Who is
it
there?
is written.
Yeah,
Sir
Abhijit.
Abhijit. Sir,
Yeah.
content can't be displayed.
Is it for all of you?
No, sir.
Okay, Sumit, you want to
Yes, sir.
continue?
No, sir. You asked the question that is it all of you with all of you? That is why I'm told. No, it is
No, no,
being shown
that
in
is
my.
fine. Like previously, I think you involved in the discussion for this.
Yes, sir, why I could, what I could recall
See,
is that
okay, uh, please wait.
yes, sir.
I want you to involve in this discussion. It's not like if you don't know, you can't try. Okay,
Yes,
at
yes.
least you
Okay,
can involve yourself in the discussion so that we can have a exhaustive discussion on any particular aspect. Because
yes, sir.
I'm teaching over from this way, this side. I don't know, like how much you are understanding. So if you will involve in the discussion, then it would be much better. Our discussion would be much fruitful overall.
Yes.
Yeah, please continue, Sumit.
Sir, for longer wavelength to be sensed, we actually need the sensors which have large apertures. So to sense a longer wavelength, that is why we need larger areas. Actually, because for shorter wavelength, for suppose there is a geographical features which have shorter wavelength, which can be emitted from a small area only. But for a physical feature which is having a larger wavelength, it for capturing the radiation, we need to have the radiation of larger areas and as well as the larger that apertures of the sensors.
Yeah, um, good. Uh, Anyone else would like to participate in this discussion? Should I call the name? Sudhir,
Sir,
I
I
would
think
like I would like you to respond.
yes, sir. Sir,
Yeah,
I think
okay.
in longer wavelength, sensing in longer wavelength, we need a larger area because it will give a accumulate response from the Earth surface, sir. Otherwise, small object it will imitate the different kind of reflection. So if it will be a big area, it will get accumulate like thermal response or temperature. These
No,
will
no.
be
See. Uh, Spatial coverage and coverage within the wavelength. These two are different parameters. Okay. First one is the spatial coverage of the sensor.
yes, sir.
On the ground, what is the smallest ground area element that is sensed?
Hmm.
Fine.
Yes.
And what is the bandwidth of the
Hmm.
spectral band within that it is sensed? These two are different aspects. Okay.
Yes.
So here I am focusing on the spatial parameter,
Hmm.
that is ground smallest ground area element that is uniquely sensed to assign a DN number.
Yes, sir.
You are correct in that aspect.
Okay.
I'm giving you 5 minutes time, all of you, and kindly rethink. We have done enough discussion for this. Okay. Now I expect response from you. So take your time, just think again, and try to respond.
Sir, may I speak?
Yes, please continue.
Sir, suppose we have a certain picture or certain anything which needs a 10 unit amount of energy to give a
Yes, could you discuss with the shared figure? Person figure face is there. Okay, so there are two images.
yes, sir.
The first
Yes,
one
sir.
is
Suppose
pixelated, but second one is more clear. Yes, continue.
yes, sir. Suppose we need 10 unit amount. Suppose we need 10 unit of energy to show this picture, and
Correct.
as we already know that shorter wavelength rays contain larger energy content, and larger wavelength radiations contain low energy content. Suppose we have two radiations. One is shorter and another one is longer wavelength. Suppose shorter wavelength have contains 5 unit of energy in 1 pixel, and longer wavelength have 2 unit of energy in 1 pixel. So in condition, if we use shorter wavelength, then for 10 unit amount of energy, we need just 2 pixels. 5 to the 10, that is 2 pixels. And if we have longer wavelength energy, then with 2 unit of amount of energy of longer wavelength radiation, we need actually 5 pixels. It shows that for showing that particular image with the help of longer wavelength radiation, we need large area, large number of pixels to show that picture. That is I wanted to know. So,
Yeah, correct. So further, I will elaborate it in more detail. Thanks for sharing your views, and it is correct. Uh, Anyone else would like to participate in this discussion? Would like to present his or her views? Yes, Arun.
Yes, sir. Sir, as of now, just since longer, just since last year, just because you know that uh,
Arun,
if
sorry to interrupt you. Your voice breaks.
sorry, sir, I think
There is some background noise, and we can't hear you clearly.
sir, yeah, I
Yeah,
think
same situation persists.
okay, sir. Next,
Fine, fine. So, as you see in the image, there there are two images. The first one is pixelated version, while the second one is more clear. Okay, the pixelated version means if we consider your camera automatically divide that human face, this particular person face, into the grid. Okay, so the smallest area within the grid is large in the first one compared to the second. Okay, even the second one is very fine. We can't distinct the area element for which the pixel value is assigned to our eyes. So they're very small compared to the first one. Okay, why it happens? Okay, if let's say consider the first image, okay, and consider one smallest area element in the gridded version. Okay, so the smallest area element that represent over here the square block. Okay, for this you can see the uniform color. It is painted by the uniform color throughout. It means for entire area a unique digital number is assigned. Okay, and it represents that area on the human face in this case. Similarly, you can consider the same area size on the same type of area on the ground. Okay, so the satellite's sensor look towards ground area. Okay, and that sensor automatically divide that area into the gridded form as you see in the image first. Okay, and each area, each grid area energy, each grid area is considered, and energy coming out from that area is sensed. Fine. So let's say first you have a two type of sensor. The first one is designed, let's say, in red band, and second one is designed in mid infrared band. So the two category of sensors are there, designed at lower wavelength, red band, and mid infrared at high wavelength. Fine. Now we first consider the first case, the sensor designed in red band. Okay. So let's say what that sensor does. That sensor automatically divide the area, okay, into the gridded form, and total amount of energy that is coming from one particular grid, okay, is sensed. Okay, and that energy that is reflected or radiated from that grid is sensed in red band. So obviously all the objects which reflect or radiate the energy in red band, and you know that in red band the photon energy is more than thermal infrared band. Okay, and we also fix the area. It's, let's say it's a 2 meter square area. Okay, 2 meter square area. Okay, and energy that is coming out from that area, let's say that is 10 joule. So from that 2 meter area, 2 meter square area, energy coming out is 10 joule, and at the sensor level there is a threshold. If energy is below 8 joule, that sensor can't sense. I'm talking about the first case. Okay, that is in red band. So though this is a more than 8, it is 10. So it is sensed and equivalent digital number is generated. Okay. Now what happened? The same area element of size 2 meter square is sensed by the sensor that is designed at longer wavelength in thermal infrared band. Then what will happen? The 10 joule energy that is coming out from that entire 2 meter square area, it will not be 10 joule. Okay, when we consider the longer wavelength, it will be less than that. Okay, the reason is very clear. Like at longer wavelength, one photon energy is less compared to the shorter wavelength. So in thermal infrared band, that energy will be not 10 joule. Okay, it will be less than that. Let's say it is 4 joule. Okay, now when it is 4 joule, and sensitivity, that again that thermal infrared sensor requires, let's say, 7 joule of energy, but it is less than that, 4 joule. So it is not more than 7 joule. So what will happen? That is not sensed. So what modification we need to apply to increase the energy, that is 2 meter square for thermal infrared sensor, the energy generated is 4 joule, but requirement is 7 joule. To compensate 3 joule to cross the threshold, what can be done? The 2 meter square area needs to be increased. Let's say it should be 3 meter square. Now when you consider the large area, then obviously the large amount of energy will be generated, will be emanated from that area. Okay, now if it is 3 meter square, then it compensate the requirement up to 7 joule, and let's say now we are getting 8 joule. Okay, so now it will cross the threshold and equivalent digital number is generated. So this is the reason why to sense the longer wavelength, we need to have a larger grid size. Is it okay? Similarly, this is one aspect. We also consider over there the reflectance of the material. There might be possibility like at shorter wavelength, the same material reflectance is less compared to the longer wavelength. So that will also comes into the picture. It's not a single variate problem, it's a multivariate problem. But in this case, if we consider that constant, like energy varies only with respect to the area, we are not considering the other aspect. Then in that case, you need to increase the area to generate the image at longer wavelength. So we have discussed in detail the implications, like at longer wavelength, the energy will be less compared to the shorter wavelength. And this is the reason why to sense the ground area or earth surface area at longer wavelength, the grid size should be larger. The large area should be viewed within a particular grid. So I'm just stopping for 3 minutes. So we'll again resume the session after 12:03. Okay, right now it's 12 p.m. So we'll again start at 12:03 p.m. Okay, so Arun, I think you have rejoined recently. Now you can try if there would not be problem at your site specifically.
No, sir. I'm
Yes.
just it's visible all things, the slide and all.
No, fine. Like you wanted to say something sometime before. Now your voice is clearly audible
No,
regarding
sir.
this point.
Yes, sir. As you say that about the pixels, sir. If you take two pixels, one is lighter in color, another is a little bit darker. Sir, can we say that the lighter one is a higher wavelength as compared to the another one?
No, not like that. See, as you are also doing in the laboratory, you are visualizing the single band image. Okay. So in the while visualizing the single band image, different sets of gray color is assigned. Okay. So different sets of gray color. Lighter image means the shade is close to white. Darker means shade is close to black. Correct. So when we have a two pixels and they are painted lighter in color, lighter in tone, and darker in tone. So lighter indicate white. White means higher digital number. If you see the mapping, digital number to set up grayscale mapping, then for the low DN values, we assign dark color, like dark sets of gray colors. But for the higher digital number close to 255 in 8-bit image, we assign the lighter sets of gray colors. Okay. So in this case, lighter is low DN number, darker is high DN number. And low DN number means less energy, high DN number means high energy. If we see the backward flow of this color assignment from the sensing the ground element, sensing the grid. So if we move from color assignment towards the energy coming from a particular grid, so light color, high DN number, high energy content, high reflectance from material in that particular wavelength. For the dark color, dark sets, then low DN number, low energy content, low reflectance from the material. So there is a direct relationship. Okay. So to understand the energy generated from the sun, we need to discuss certain radiation principles. Okay. And we also need to understand the background of energy sources like sun in this case. Okay. So we know that visible light is only one many forms of electromagnetic energy. Okay. We also have radio waves, heat, ultraviolet rays, and X-rays. They are the other similar forms of electromagnetic energy. Okay. But see, all these energies is inherently similar and radiates in accordance with basic wave theory. Okay. So they are radiated by the particular source in accordance with the basic wave theory. Wave theory means they travels with the speed of light and c is equal to nu into lambda. Okay. And when you see this, then the wave theory, this theory describes electromagnetic radiation as a traveling, okay, in a harmonic sinusoid fashion at the velocity of light c. If you analyze the wave theory, okay, so magnitude of that energy travels from source in a particular direction with the speed of light, but that amplitude vary in the fashion of sinusoid or cosinusoid. Okay. And if you consider the one particular variation, okay, from one particular peak, then down, so upward and downward peak, so there will be the distance from one wave peak to the next is wavelength lambda. A number of peaks passing a fixed point in space per unit time is the frequency nu. Okay. So further discussing in this context, when sun is considered as energy source, okay, so what happens due to internal processing within the sun? It's a nuclear fusion. Okay, tremendous amount of energy is generated. Okay, and that due to that generated energy, the surface temperature of sun increases. Okay, and due to increase in temperature, what happens? The equivalent amount of energy is radiated back. So temperature can be correlated with the total amount of energy that is emitted from the source. And they are related. M is equal to sigma T to the power 4. It is called the Steeman-Boltzmann law. So we consider that object as a black body. Okay, it's a perfect radiator. And due to some internal mechanism, tremendous amount of energy generated. And that generated energy is quantified in terms of temperature of that material. So in this formula, M is equal to total energy exitance. It is measured per watt per unit area. So total energy exitance from the surface of a material. Okay. And T is equal to absolute temperature in degree Kelvin at that material surface. And sigma is Boltzmann constant, and it is measured watt per meter square, and degree Kelvin power minus 4. Okay. So energy emitted is primarily a function of surface temperature. So this formula is valid for any material that is having surface temperature more than 0 degree Kelvin. It means if we consider ourselves, we consider the our surface material, so all of them have a temperature more than 0 degree Kelvin. It means all of these materials are radiating the energy. And if you consider in the energy forms where we discuss, there I said that all the material, most of the material radiates their own energy. And they are also one form of the energy source. So active system where they have their own energy source, sun we consider, and all the materials which radiate the energy, they are also considered as an energy source. Okay. Now similarly, just see over here, the energy is dependent on the temperature. Similarly, the radiated energy is also dependent on the wavelength. Okay, that radiated along with the temperature, the radiated energy varies with respect to wavelength. It means the radiated energy component at red band, in red band, and radiated energy component in green band, they are not same. So that's why spectral composition of energy emitted is also a function of surface temperature. Okay, and when we talk about the spectral composition, it means that total energy emitted also varies with respect to wavelength. Okay, so when we analyze the energy variation with respect, previously we have seen that energy variation with respect to temperature, M is equal to sigma T to the power 4. Now we are discussing energy radiated variation with respect to the wavelength. Okay, and there we measure one entity over here, that is at what particular wavelength the radiated energy is maximum. Radiated energy varies with respect to wavelength. Okay, when we analyze that particular curve, so there we define an entity, that is at which particular wavelength the radiated energy is maximum. Okay, and it is computed with respect to by using the Wien's displacement law. Okay, and Wien's displacement law tells us that the dominant wavelength lambda m at which that particular material radiate the maximum energy is also the function of temperature. It is equal to A divided by T. Here again A is the constant and T is the surface temperature of material. Okay, and the dominant wavelength at which the radiated energy is maximum is inversely proportional to the temperature, surface temperature of the material. Okay. So these two formula are depicted in a common diagram over here. Okay, there you can see that on the dependent axis we have the energy component, that is a spectral energy radiance, spectral radiant excitance. Okay, means at a unit wavelength per meter square how much amount of power is radiated, or how much amount of energy is radiated per unit wavelength. Okay. And you see that this curve indicates the variation of energy, and on the independent axis we have the wavelength. So with respect to change in the wavelength, how the radiated energy, spectral component of radiated energy is changing. And we also define the peak in this plot. Okay, so by selecting the first formula where we define m is equal to sigma t to the power 4, we select the temperature. So in case of sun, the surface temperature is 6000 degree Kelvin. And the first plot, if you see, the visible radiant energy band, sorry, if you consider the first plot where we have the highest peak, okay, that is for the sun at 6000 degree Kelvin, and just see how it varies with respect to wavelength. So energy radiated from the sun, okay, and sun surface temperature is considered as 6000 degrees Kelvin constant. So that radiated energy varies with respect to wavelength. Similarly, if you see at 300 degree Kelvin, the plot. So this plot tells us how the energy radiated from Earth, okay, changes with respect to the wavelength. We have a lot of analysis based on this particular plot to understand the sensor development, sensor design, and in which band we acquire the images, radiated energy component, reflected energy component. There will be the detailed analysis and detailed description of all these parameters. Like 3 points have already given in the slide, like sun emitted and radiated, these two terms are same. So sun emits maximum at 0.5 micrometer, and it can be seen in this plot. Just see this vertical bar over here. So it is called as visible radiant energy band. Okay. So in this particular band, that is centered at 0.5 micrometer. I hope you can see this vertical bar in this diagram that is shaded with gray color. Okay. So this vertical bar, and if you see how much portion of radiated energy curve from the sun falls in this bar, then the peak of that particular plot falls in this bar. Okay, so plot of 6000 degree Kelvin, the peak of that plot falls within the visible spectrum. how much analysis you have based on this? What you can, how much like information you can figure out based on this plot and this discussion, like the visual radiant energy band, the peak of the 6000 degree Kelvin falls within that band, and it is centered at 0.5 micrometer. Based on this analysis, could you explain why our eyes are sensitive only within visible band? Could you correlate? Why not human eyes are sensitive in thermal infrared band, near infrared band? Why they are only sensitive in visible band and they discard all other energy outside the band? Through the physics, concept of physics, through the science, we have concluded this analysis. Okay. Now, if we discuss the design of our sensor organs, eyes, okay. So let's see, there is a direct correlation from the sun, the maximum radiated energy within the visible spectrum, and even further, you will see that within this spectral band, I'm talking about the visual spectral band, energy is passed through the atmosphere without significant loss. We'll see it later on. Okay, and nearly whatever the energy that is radiated from the sun, the nearly the equal or somewhat less, it's not equal, less than that, but most of the energy content reaches to the Earth's surface. Okay, they are significantly reflected back. Okay, and our eyes are sensitive in this prominent band where the energy component is maximum. So all it is nature. Okay, our eyes are sensitive in that particular spectrum, in that particular spectral band where the existence of energy is maximum across all bands. Just see, if you go away from the if you analyze this curve, so outside of this in this visible radiant energy band, even the smaller side or larger side in terms of wavelength, energy decreases. Even if you go towards ultraviolet, cosmic, gamma rays, what it shows that energy is less. While if you move away from there towards higher wavelength, the energy again decreases.
Hello, sir.
Yes.
If, sir, it is based on evolution, actually. If humans actually need to see UV or IR radiations, they would have evolved to see that.
Oh, no, that is correct. What I'm trying to portray over here, we are just exploiting the maximum energy available. Obviously, if we evolve to see in microwave band, so we could, but in microwave band, the available energy is less. I'm trying to correlate from that context. Like from the sun, the maximum radiated energy is lying within the visible spectrum, and Earth atmosphere is also behaving as a perfect, you can say, kind of transparent medium. We'll see it later on. Atmosphere also behave as a transparent medium where that entire energy passes through without significant losses and reaches to the Earth's surface. So there is total the positive environment, you can say, okay, positive environment to allow the entire energy to pass through from that originate from sun in the medium reaches to the Earth's surface. Okay. Now this is one of the interpretation out of many. Now the second one, that is Earth emits maximum at 9.7 micrometer. That is a thermal infrared. Okay. So when you are going and just see the radiated energy component from the Earth's surface starts somewhere from 3 micrometer. If you see the 300-degree Kelvin curve, so as we discussed before, m is equal to, that is m is equal to sigma t to the power 4. So applying that formula, any object which has temperature more than 0 degree Kelvin starts radiating the energy. Okay, it is valid for Earth also. So at 300-degree Kelvin, Earth radiates its own energy and acting as an energy source. Okay, but that is a radiated energy component, and that radiated energy component starts from 3 micrometer. It means below 3 micrometer we don't have the radiated component. So this is also one of the benefit. Like below 3 micrometer, all the energy which we see, they are the reflected energy component. Okay, so there is not mixing of radiated plus reflected both. So below 3 micrometer, the pure reflected energy signal we sense. Okay, but this is the reason why you can see that in multispectral sensors, the bands which are designed, okay, they are mainly lie between visible spectrum till 3 micrometer. Okay, we also design the sensors in wavelength more than 3 micrometer. So it is there. So this is the second interpretation based on this plot. And third one is obviously this 3 micrometer dividing line for the reflected and emitted infrared from the Earth. So you can say less than 3 micrometer, the energy which is coming out from any area element, that coming out is only constituted by reflected energy component. Okay, if we are sensing energy within in a spectral band less than 3 micrometer. Is it clear? So I expect you to write it in your note in detail, the discussion we are having right now. Okay. Fine. So now I request you to go through the content which we have discussed in 1.5 hours. Okay. So in the remaining half hour, you are going to revise it and make a note on that. Okay. And if there will be any query, you can ask. So